Hello. You look like monks. All right. Good morning, everyone. Welcome back. So, just a small recap about what we did during the last lecture. So, we are starting to investigate. We already started. We are in a good position in our study of the dynamics of dark energy, dynamical dark energy, and we investigated the quintessence model, meaning dark energy is an ideal fluid. Under these assumptions, we investigated the Klein-Gordon equation for fields in general, for a scalar field in general, and we have seen that we have various scenarios. Could be matter, could be lambda, and so on and so forth, according to how the ball, right, is rolling into the potential. So the potential determines the behavior of this scalar field. And the conditions that we used are slow rolling. So for the slow roll condition, right, where the kinetic term is much smaller with respect to the potential one, then we see that dark energy, the equation of state of dark energy, is very similar to the one of lambda, but not quite. Okay? So in terms of behavior, our equation of state is similar to the one of lambda, but with a major difference. One is which phi is going to be smaller than, larger than -1, meaning minus 0.90 something or 80 something. It's important that it is within the error bars of current measurements for the interval of time range that is covered by observations. Okay, so we don't cover the entire history of the universe, but we have good constraints on the equation of state parameter, at least in terms of lambda, between at low redshift, from low redshift probes, such as galaxy clusterings, galaxy clusters, and so on, and higher redshift probes, which is sort of 1, because it's just the cosmic microwave background, right? Redshift 2000. These are the two strong solid constraints that we have on omega lambda. Therefore, we know that we have to be not too far from -1, but still a little bit larger. And even more importantly than the value of the equation of state parameter, also what is extremely important is that this guy has a time evolution. It's dynamical because the ball is rolling. Therefore, the equation of state parameter is going to change as a function of the cosmic history. Then, what we start to do is to investigate the dynamic of the field itself, therefore to see how the potential is changing as the universe is evolving. And to do that, we had to consider the Klein-Gordon equation, which is the field equation describing the dynamics of the field phi. So that's the equation of motion of phi. And we see that there is an H contribution in this equation, and therefore we need simultaneously to use the Friedman equation to constrain the behavior of H given a certain phi, And we know that H depends on itself. Therefore, this is going to be a system that has to be closed. Right? In our Friedman equation, we have the contribution of matter, and again with matter, I stress it n times because I know it's prone to mistakes. This could be proper matter, like dark matter or baryons, or could be radiation or relativistic species in general. Okay, so we are considering one of these at a time at the moment. Okay. Then we have seen that to investigate this system of equation, it's very convenient. I mean, there are numerical solutions in general, so you don't have an analytical expression that tells you phi of A equal to something. You don't have that. Okay, so we have to solve it numerically, but we can study specific set of solutions for this Klein and Gordon equation, which are called the critical solutions, right? These are solutions for which we identify the new set of parameters and they are not evolving as a function of time, okay? So what we did, we start with our Klein-Gordon equation, with our Friedman equation, and we identified the new variables, x1, right, which was proportional to phi dot, and x2, which was proportional to the square root of the potential, okay, just a change of variable. On top of that, to simplify ourselves, we investigate the evolution of everything, not with respect to the expansion parameter or the proper time or whatever, but in terms of number of e-foldings, which is just the logarithm of A, just simple as that. Therefore, we made a new change of variable, if you wish, for the time, in which we are expressing everything in terms of n, and therefore so derivatives with respect to n, instead of derivative with respect to the conformal time or A. Okay? That's what we did. Then, as I said, making our life simpler, we transformed these one second-order differential equations into two first-order differential equations, one of which is the derivative of e prime of x1, and with prime I mean derivatives with respect to n. Okay, we have seen that, which is going to be an expression of x1 and x2. Okay, so some complicated equation, but bottom line it was a function of x1 and x2. Same goes for x2, again time derivative, again another equation which is a function of x1 and x2. Okay. In doing that, we identified two new functions. One is gamma, and one was lambda, and the other one was gamma. Where lambda was characterizing the steepness. Okay, so the first derivative of the potential in our dark energy equation, in our description of the fluid, so the potential, and tell us the exponential steepness of our potential at a given location. Okay? Whereas gamma, at that location, gives us what is the curvature of the potential. Okay? That's very convenient because V could be of several shapes, we have several forms, but if we characterize everything in terms of these two parameters, it doesn't matter the specific shape of this one. Everything just depends on these two guys. The behavior depends on that. Okay? Once we have that, we look for the critical solution, which, as I said, are special solutions for which these variables are not changing. So, and we have seen that when we impose this condition, you know, we used a perturbative approach. To linearize our problem. Okay. Once we linearize our problem, then everything is described in terms of a transformation matrix, which can be linearized and give us two eigenvalues. Two eigenvalues that tell us what is the stability of the solution at those locations. Okay? So you see, given this, you have a derivative equal to 0, it means that you are or on a minima. This would be corresponding to a stable solution, where these two guys are both negative, and we have seen why with negative, both negative eigenvalues, this is a stable solution, okay? Therefore, if there is a perturbation, if we are there and there is a perturbation, the system, whoop, 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 goes back to that location, okay? Then it might be a maxima, this is an unstable point, which occurs when these two guys are positive. Remember that in the linearized equation, after the perturbation approach, we have a solution which has an exponential, and if we have two positive numbers in the exponential, then if we are there, boom, we run away, okay? Unstable solution. Or the two signs can be opposite, one can be positive, the other one can be negative, then we are in a saddle point. And this means that we kind of have stability along a direction given by one of the two negative, one of the eigenvectors which has a negative eigenvalue, so we are stable in this direction, but we are unstable along the direction of the other eigenvector, okay, which has a positive eigenvalue. And therefore, the behavior of the solution in those surroundings is sort of an attraction, okay, we are falling into the minima, but then boom, we are repelled away. Okay, so we tend to go there, we kind of stay there for a bit, and then we go away. All of these are important critical points. Not much the unstable one, because the universe is basically not going to spend much time there, if at all, okay? Because it doesn't, there is not the tendency to go in that direction, okay? The other little bit of information that we got is that these two guys, the eigenvectors, could also be, have a complex component, okay? This, in the solution that we have seen in our perturbative approach, means that we have sinuses and cosinuses in our solution, okay? Which together with, for example, a stable solution, so we have the absolute value of the separation between the critical point and our solution, which is decreasing because the exponential has a negative power, therefore goes down very fast, but there is a cosinus and sinus, and therefore the solution is sort of a helicoidal shape, okay? Good. Given that, we kind of have the power to describe sort of everything, okay? In terms of the phase space properties that we described the last time, okay? So, what we are going to do now, after having seen this general description, so we have our x1, x2, we are start to look into actual solutions for our cosmological model, okay? So let's start the phase space that we derived last time. So it's variable solutions we have seen are the one within this half circle with radius 1, okay, in x1 and x2 phase space. That's because if we are in this location, omega matter would be negative, and this is not much meaningful, okay? Whereas omega positive occurs only within this half circle. Moreover, I mean, omega positive will be also here, but we don't accept this solution because otherwise the potential would be negative, and that's not what we have in the first place, okay? With potential for dark energy is positive, and therefore we are constrained in this regime. Good, let's give a look now at the stable solution. Again, I remind you that we are dealing with one matter component and a scalar field, okay? That's the scenario. That's why we have a two-dimensional phase space. If we would introduce a scalar field, dark matter and baryons, and radiation, so if we would split this matter contribution into separate fluids, then the phase space would be three-dimensional. Okay? At the end, I will just show you very briefly what would be the solution, the full solution, given three species. Okay? Now you can think yourself that we are in a matter domination epoch, for example, and we are looking how the universe is evolving from this moment on. Okay? You can think in two different regimes. You can as well, if you want to study what's happening in radiation domination, again, this rho m would be the one of radiation, and then you see how the system evolves. Okay? We cannot join the two together because we are keeping them into different separate regimes, okay, of domination for rho m. Later on, when we introduce a third dimension, we are going to we are going to see all the history of our universe. Okay? Good. Let's keep this guy here, and then slowly we are going to fill it up. Now, these are the equations that we have seen the last time, okay? And we have these additional parameters, right? So, sorry, these are the equation 1, equation 2, and we have these two guys that depends on phi. There is a dependency on the potential, there is a dependency on phi. And therefore, these two guys could change. Okay? They're not fixed numbers, but they can evolve. And therefore, to close if this guy is going to evolve, this is going to be extremely relevant to study the solutions of our set of equations. But if this guy evolves, we need another equation. Okay? And therefore, we need another lambda prime equation that we have seen the last time. So we have 3 equations to solve our system, and gamma follows. Okay, there are certain approximations. We are going to look at gamma later on. Okay. Now, as a first step, we can ask ourselves, okay, what happens if I have lambda constant? Okay, is it referring to a special potential? Is it always the case? It is not. What's happening? So let's get the third equation that I wrote there. So we have lambda prime, that I recall you, is the lambda over the n. Okay, so prime is derivative with respect to n, is equal to minus square root of 6 lambda square gamma minus 1 x1. Okay? Then what we can do? Well, let's see what's the meaning if we want lambda to be constant. Lambda constant will mean that this guy is equal to 0, right? This is just a number. This is just a number which is 0 or positive, not much interesting. This one is going to be a number positive or negative or 0. So in gen is a number that is ranging between minus 1 and 1, but this guy could set the fact that gamma is always constant, so this term is equal to 0. Okay? So if this condition is met, then lambda is constant. Gamma equal to 1. Okay? Let's see. Gamma equal to 1. Okay? Now let's go back to the definition of lambda. Lambda is defined as minus, so there is a minus in front. And then we have the derivative of the potential with respect to the scalar field phi, divided k is just a number with the 8 pi g factor thing, divided with respect to the potential. Okay? Now, if lambda is constant, this can be just solved very easily, right? Because v, let's spell it down, the derivative of v with respect to phi is d over the phi, and then we have times 1 over kv. That's a constant. We can separate the variables, and we can just integrate this equation to get the solution, right? Therefore, if we do that, so I separate the variable, the v over v equal minus k lambda lambda the phi. I just integrate over v, I integrate over phi, and I get my solutions for the potential. Therefore, v phi is equal to v0 e to the minus k lambda phi. So that's the case for a very specific potential. Okay? Here I went asking myself what happened when this is constant. We have this potential. I can think the way around. If I assume in my dark energy model to be described by such a potential, then lambda is constant. And gamma is equal to 1, fixed. Okay? So, what I'm going to study now is the solution for lambda equal to constant. And we are going to look at all the critical points that refer to this situation. Okay? So, how do we do it? We now know that V is this guy, is not anything else. we have the value of lambda and gamma, so this guy are known. What we do, here there is going to be all our quantities, x2 that depend on v, this is known, this is phi, and we can just solve it and get our critical points, okay, with the procedure that we've seen the last time. Okay, good. If we do that, we get a pile of critical points. Let's try to do like this. So it's going to be quite a big table, okay? So critical points for lambda equal to constant, which meaning the potential to be of an exponential form. Okay, that's the case we are going to investigate. So, let's see. We are going to have x1 and x2, so these are going to be our critical points. Okay. Which one of our critical points is going to be 0, 0. It's sitting here. So we have a critical point here. That's our critical point A. Then you know that once we define this x1 and x2, right, we know that everything depends on that. For example, we can characterize omega m, and this is a function of x1 and x2. We have omega phi, and this is a function of x1 and x2. And we have the equation of motion of the potential, again, is a function of x1 and x2. Therefore, wherever I put the finger in this plot, I know instantly the properties, the density contours of the matter field and of the scalar field of dark energy, and the equation of state of dark energy. Okay? So now I put my finger on A, and I know what is omega phi. Omega phi is equal to 0 for this case. Just look at the expressions that we derived last time, that's just equal to 0. Very simple substitution. Just fill up the number 0, 0 into your expressions there. W effective as well, we can also get W effective, which is the one giving the dynamic of the universe, given the combination of matter and the equation and the dark energy. And our effective equation of state we find out to be the one of matter. Okay? We have a matter-like dominated epoch. Then we have omega phi, and this is undefined. Okay? This is not defined. We are in matter domination. Then we can ask ourselves what is the stability of this critical point. Therefore, we look at the eigenvalues corresponding. And we are getting 3/1 minus Wm. And then we have mu2, which is 3/1 plus Wm. If we are in matter domination, these two guys are, for example, 0. Wm is equal to 0. Therefore, we have minus 3/2 and 3/2, negative and positive. This is a saddle point. Stability. This is a saddle point. We have mu1 times mu2 is equal to minus 1. One is positive and one is negative. Okay? Then we have another critical point. I will call it B1, like in the script. 1, 0. Let's make it a little bit smaller, the table. 1, 0. And this is 1, 1, 1, and 1 as well. Okay? So we have we are going to have that we are in a field-dominated epoch. So you see, omega phi is equal to 1, not equal to 0. Assuming flat geometry, it means that we are in a field-dominated. Omega m is equal to 0. right? We are in a field-dominated epoch. W effective is equal to 1, and W phi is equal to 1. No surprise, because this is the guy that leading the expansion of the universe, okay? Then we can ask ourselves about the critical point, and we get 3 minus square root of 6 over 2 lambda. 0, 1, this 1 is off too much, sorry guys. 3 minus square root of 3 over 2 lambda, and 3, 1 minus W m. Okay? And this is going to be, you see, we have a condition where this is going to be always positive, because Wm is or 1/3 for radiation or 0. Therefore, this is positive. But this can change sign, and it changes sign according to lambda. Okay? Therefore, this could be or an unstable point, if lambda is smaller than the square root of 6, because this would be smaller than 3, meaning this is a positive number, unstable point. If it is otherwise the way around, we have a saddle point. For lambda larger than square root of 6. Okay? Then we have another point that I will distinguish from this point B with 2, so B1 and B2, and this guy is on the other side, minus 1, 0. And again, we have 1, 1, 1. With, again, some values for the eigenvalues. Okay, look at the table, and I'm not going to copy everything, but you see, you understand the logic here. Okay, you first identify your critical point. You find one guy here. Once you know x1 and x2, you can fill up your table. You just plug in x1 and x2 here, omega equation of state effective. Okay, and you do like that for all the parameters. Therefore, our B1 is going to be here, and our B2 is going to be here. Okay, let's look at these guys. W effective or W phi equal to 1. That's a peculiar one, but you shouldn't be surprised, because when we looked at the possible scenarios for the solution of the dynamic of the Klein-Gordon equation, we have seen that we can have indeed have a fluid which has an equation of state equal to 1. And what's happened if the equation of state is equal to 1? Let me write it here. Well, you have you know that basically you have the continuity equation, where you have rho, which is proportional to E to the minus 3, 1 plus W. Okay? What's this? Plus W. Therefore, you can plug in your equation of state parameter. You know what is the evolution of the density, right? And what happens if I plug 1 here? I have 3 times 2, which is minus 6, e to minus 6. Boom! The density goes down. So if we have a fluid of this sort in that points, this is going to die out. Okay? Then what happens? So this is unstable or a saddle point. So if we are in the case of stability, so I took a precise number here when I draw everything. Which is, I think, for lambda equal to 1, therefore this would be unstable. And what happens? Our solution, boom, running away from these points very fast. So we are going to have, if our initial conditions are putting ourselves in this regime, we have this fluid which is dying out very fast, and is going away from these sort of regions very, very, very efficiently. Okay, so we are going to run away from that. Whereas A is a saddle point. Therefore, we know that our solution could be, for example, something like this. Tuck and tuck. Okay? And here are escaping somewhere there. And it depends what happens on the critical points in the rest of our phase space. Then we have an interesting one which is extremely interesting, which is the critical point that I call C, and which occurs at lambda equal to lambda over square root of 6 and square root of 1 minus lambda square over 6. That's this equation. That's our critical point, where, let me copy this one so that I can over 3. Okay. We are going to have this guy, if lambda is equal to 1, so you see this is the location in our phase space, with lambda equal to 1, it's roughly here. Okay, so you see, this is not symmetric in the end. The solutions are not going to have a symmetric pattern, even though we start with these fixed points that are going always to be there, but can be, according to where this guy is going to be, the solution is going to change, to go somehow in this direction. Okay? Good. Then, look at this. This is interesting, because if we look at the equation of state parameter, omega effective and omega phi, you can see that we can have a lambda-like scenario. Look, effective equation of state parameter minus 1 plus lambda square over 3. What's happening if lambda is very small? That's very close to minus 1. It's very close to the cosmological constant. Ooh, that's an interesting point. Okay, that's an interesting one. And of course, you see that the two guys are equal, the effective one and the one of the field, because it is a field dominated. So we can end up, let's say, in the far, for this point, represent the far future, where the dark energy is going to be the ruling species in the universe, because its equation of state is going to be close to minus 1, meaning rho, following this equation, is not going to change. The other ones, matter and radiation, are going to die out. The density, the universe is expanding, density of matter and radiation going down. This guy, because if lambda is very small, is going to be constant and is going to become dominant. So that's the far future. Okay? Stability, same business. We are going to compute the stable and to investigate the stability point. So one eigenvalue is 1/2 lambda square minus 6, and the other one is lambda square minus 3, 1 plus W's m. And we see that we can have a stable point or for lambda square smaller than 3, 1 plus Wm. So we have a stable point, meaning we must fall there. Okay? Or we can have a saddle point. No, that's for the saddle, sorry. Positive and negative. Saddle, and this is stable. Stable. And that's the case for 3, 1 plus Wm minus lambda square algebra 6. Of course, we want our eigenvalues to be also within the regime that we have described. So you see that we can have a stable point if lambda is equal to 1, omega m is equal to 0. You see that's going to satisfy this condition. Okay. If lambda would be okay, that's it. Okay, good. Then we have the last saddle point. Sorry, the last critical point, which is the critical point D, and this is going to be at the location, at some location, okay? Now I don't copy it down, look at the table. And it has a certain equation of state, this I write it down, sorry, a certain value for the density contrast of the field, and we discover that the equation of state is better like Wm and Wm, okay? So it's going to be a field with the same equation of state of the matter one. So you see that if we are in the conditions in which we are living nearby this point, the density of dark matter and the matter component are following each other. Okay, that's a scaling solution that I mentioned at the beginning of the lectures, right? Remember that there was this coincidence problem, why today omega lambda, omega dark matter in this case, and sorry, the omega lambda, the omega dark energy and omega matter are very close one to each other. Well, because we can have a scaling condition of this sort. The two are following each other. Okay? Good. Then we are going to have, certain the eigenvalues can be positive, negative. In this case, we have, I don't write the conditions, but we have, we can have, I mean, it's more complicated because we can have a saddle point, we can have a stable point, and we can have an unstable point. Okay? So it's a little bit more complicated. And therefore, we can have also the D point within this plot. But if I choose lambda to be equal to 1, D would be outside. It's non-physical. We have a mathematical solution. So in our phase space, we have a D point which is somewhere. But what happens? It happens that it's non-physical. Therefore, it has no meaning. That's the other concept that you have to take home. If you find your critical points, they must have a physical meaning. Maybe mathematically they are fine, but they must be, my respect, our understanding of physics. Okay? Good. Okay, what else I wanted to say? Well, one thing that I could say is that now I don't write down the equation, but among the eigenvalues there is a square root. And one of these guys could be, under certain condition, a stable helicoidal solution. Okay, so be a stable spiral, it's called. Okay, it means that we are not falling like that. Okay, but if, for example, for a different kind of lambda, we would have, I don't know, D in this location, the solution would do something like that. Okay, that's because one of the mu's, one of the eigenvalues is complex, because there is a square root, and what is inside the square root can be negative, meaning one of these guys is complex, has a complex component. Okay, all the others are real. So the only one that can be a spiral stable point is the point D. Okay? One last thing that we should look at is if we are in the vicinity of point C, or point C, which is the interesting one because we want a dark energy, lambda-like behavior, okay, is what are the conditions for having acceleration, right? Therefore, when this guy is larger than minus 1/3, okay? Therefore, in this case, let me put it here, for the point C, where we want acceleration. Let me go back to our A. which is up here, A. So it's going to be our solution for lambda equal to 1. Let's remove the d case. Then we are going to, no, that's called C. When we have acceleration, well, we have acceleration when W effective at the location C, so in this point, is smaller than minus 1/3, right, acceleration. And yes, we are in the right location, because when we study the general property of the phase space, we know that the region of the phase space where we have acceleration is this one. And yeah, of course, we are in the right location. We have acceleration. We have all what we need. Okay? That's a good cosmology. Okay, nice. Therefore, I repeat again the properties of point C. Let me bring it up here. So up C runs along the circle. That's what this guy is telling us. That's around the circle. It provides us an equation of state that for lambda going to 0 give us something very similar to the cosmological constant, but a little bit larger. For our W phi is in the range of -1, but slightly larger. That's what we're searching for. That's why people is getting crazy with, Euclid, Eurozeta, and LSST, and all these gigantic surveys to see if we get a value which is smaller than -1. So far, that's not the case. Okay, if you look in plots that are, I don't know, just randomly, omega m and W and W, then you get some banana plot, and your -1 is going to be here. So we are fully compatible with -1. If we would make our measurement better and we would find something like that, okay, then we would say, ah, damn it, it's very, very, very close to -1. But if we would find a banana, so our constraints, our error bars would point to this direction, not compatible with -1, then we know lambda is equal to 0, and we have a fluid out there in the universe, which is our dark energy. Okay, that's the game we are playing. Okay. Nice. Then you can say, oh, that's cool, but it's very specific because we are taking a lambda equal to constant, right? That's what we started with, for which we have a very specific potential, and you can say, okay, but that's not that general as we would like. Yes, but you can think in these terms. If the behavior, the way lambda is changing as a function of time, therefore if this guy is quite small, or let's say smaller, so the time change of lambda is smaller with respect to the Hubble rate, so to the expansion rate, then you have a long range of the cosmic history for your universe, in which lambda can be very well assumed as constant. Okay? Therefore, the trick would be like with thermal equilibrium, right? The universe is not really in equilibrium. It's a dynamical system, but it has the time to readjust itself and get the equilibrium. Therefore, you can assume equilibrium at all times. Here is conceptually sort of similar. The physics is very different, but conceptually sort of the same, in the sense that the universe is, yes, is expanding. Therefore, this guy might not be constant, but I have an equation that tells me what is lambda at each individual time. And therefore, I can use my Friedmann equation to derive h, and with h, I can, given my potential, set my lambda, and there I know what are the critical points. So what's going to happen if lambda is different than 0? I will get these critical points, but they're moving around with time. Okay? Lambda is changing. For a certain lambda, I have, for example, C here. Well, I'm going to show you that with a large lambda, we start here for the point C, And as lambda is getting smaller and smaller, we will be moving in this direction. And d, which will go along a straight line in this direction, will move on the opposite side. Will move like that. Okay, for a certain lambda. These three guys are always there, and you know that. Okay, for this potential. So, good. That's a good point where to have our break. So this is, I was slow here, I went to all critical points. I didn't write here all the numbers because I wanted to give you the concept. The concept I gave you, if you want to look at the numbers, look at the table in the script and in the lecture notes, and just play with the lambdas to see if it's true that we have a stable, unstable, whatever points for each of those, okay? And play a little bit with that. Good. Nice. Now, we have the break. After that, we are going to continue with lambda prime different than 0. Okay? And for being a little bit pragmatic or specific, we are going to assume a given potential. Okay? We'll make first a list of possible potentials that are popular, let's say, on the market. There are 4 of them that are the most popular ones. And then we will pick up one and see how the universe is going to behave with lambda different than 0. And in doing that, we will see that we have a solution that naturally evolved to a scaling solution, meaning you have a variety of initial conditions, but we end up with lambda following omega lambda, omega field, so the dark energy equation, the dark energy density contrast that follows the one of matter, or the matter component. Or you have even scaling solutions in which you are forced to be driven to the point D that becomes naturally, with the evolution of lambda, an unstable point, so you can get captured there, but then lambda is changing, and not only the position, remember, not only the position changes, but also these guys are changing. The stability conditions are changing, because they depend on lambda, you see? So you can be trapped at a certain point, so the universe is staying there, lambda is changing, oh, I'm a saddle point, I'm going to escape, okay? And we're going to see that with the components, with the full picture of the universe, we can be trapped in a certain location, and we are going to move and be attracted to see that we become stable, and therefore we must fall there, and we have the entire sequence of passages in our universe history: radiation domination, matter domination, and acceleration at the end. Okay, so it's kind of come out quite fluently out of this model. Okay, good. So let's have a break. We can resume at 10 past midday. Okay.